Now we're entering into Voice over LTE Enabling Features chapter. Charles, can you tell us how this chapter and the objectives relate to what we've already covered so far?
You know, that's a really good question because now what we're going to focus on is the LTE aspects and what are the things that allow us to make VoLTE, voice over IP, work over LTE. So we'll be looking at things like what are the bearers that we're going to support? What are the conversational voice bearers? So we're looking at quality of service. How do we do packet aggregation or how we deal with emergency calls in the network?
Charles, can you tell us about support for multiple bearers now?
First, let's look at the architecture quickly. Remember that in the architecture, the subscriber is accessing the eNode B here, is accessing the eNode B, and we're looking at the EPC core and the EUTRAN connection. So what we need to do is establish something called a bearer or an EPS bearer, which is a communication between the PGW and the subscriber. So the packet gateway and the subscriber forms what we call an EPS or Evolved Packet System Bearer. This is going to carry the data. Now, when we talk about multiple bearers, what we're looking at really is being able to establish our VoIP call over a separate bearer from our data. Now, a bearer does not mean it is more resources. It's just a higher quality of service. We are applying a quality of service to the bearer. That's what we're doing. So when we don't have it, if we do not enable this EPS bearer, we're going to be carrying our voice over what we call the default bearer, which means there's no quality of service. There's no differentiation between voice and email, for example. So you notice the actual load of email can affect voice and voice can affect email, and they can interact in a bad way. When we enable it, we will actually separate the voice from the email and be able to control the quality of or the throughput of that with higher priorities and such. And therefore we can prioritize and differentiate, and that's the word we use, is differentiate our services. So when we look at our voice, really we can break our subscriber into two types of, there's two support groups that we need to look at. First of all, we have the capabilities of the subscriber itself and the actual preferences of the subscriber in the network. So in the subscriber, the capabilities, we're going to use something called the feature group indicator, and we're going to have some bits to set for that feature group indicator. That will tell the system that the subscriber is capable of performing voice over IP. And then in the user preferences, we tell the system how I prefer voice. Do I want it to be just circuit switch, which means I have to use a non-LTE carrier, or I prefer circuit switch over a non-LTE carrier, over LTE, or I prefer only voice over IP or voice over LTE, or I want voice over LTE, and if I have at last resort, I can go to voice over CS if there's no available voice over IP. Those are the type of things that we have in the groups. Those groups are what divide our subscriber, that we have to define both aspects in those groups.
Now I understand that there's two groups. Can you give us some examples of the two groups that you have listed here?
Sure. Let's look at the capabilities of the UE first. First of all, here is the feature group indicator, and we've decoded it in such a way, and we have certain bits that need to be set. So this is sent by the UE in a message called UE capabilities. So in this UE capabilities, we have this feature group indicator, a set of bits that tell me, okay, bit 4 says I can use unacknowledged mode. Bit 8 and 9 would tell me about support for handovers. Bit 10 would allow me bits 22 and 23 would tell me if I support other technologies. Bit 28 is required for a feature we'll talk later on called TTI bundling. So for us to work VoLTE, we have to have at least bit 3 set and bit 7 set and bit 28 set for us to support it. Now, moving on to the next one, the other example, the other group is actually defined in the same message, again, in the initial UE message, in the initial message that the subscriber sends us, hey, I'd like to register with the network. We're going to we have a voice domain preference, and in that voice domain, we're going to define what I have, and for us to support VoLTE, we need to have IMS voice preferred over circuit switch voice for us to function. Now, where do we see this? Initially, we have that first message that I sent you, or that I told about. We have this random access message, and we send in an initial registration. Okay, in the initial registration, we say that's that initial UE message there, where the subscriber will send in that initial signaling and to tell me my voice preference, the second group. We perform authentication and security on the network so that we can get the appropriate encryption keys and such. And then we have an initial context setup. And in this initial context setup group of messages, we're going to ask for subscriber capabilities. So this is where the second or the first group, the subscriber capabilities, comes to the system. Now, once I've done that registration, I can't make a voice call until I perform the SIP registration that we talked about in the previous module. And I get a SIP 200 OK. At this point, I have successfully completed IMS registration in the network. Now, the voice call itself, once I've registered, now you can see that the SIP signaling, but all of this SIP signaling is flowing over an EPS bearer called a QCI5 bearer, which is for voice over IP or voice over IP signaling. So it's for SIP. Again, we separate it from the actual voice. At the end, when we establish the call, we establish a QCI1 bearer. So remember, QCI means quality of service class identifier. That QCI1 bearer will carry the actual RTP packets, whereas the QCI5 is carrying SIP packets that we saw in the previous module. So let's look at those bearers and what these quality of service class identifiers are. The quality of service are defined in 3GPP. There are 9 defined quality of service class identifiers in the 3GPP. These are the standard ones. We have the option of adding others, but for right now, we're going to focus on just the 9 that are set. There's a section of them called non-guaranteed bit rates. And notice that QCI5 is considered non-guaranteed bit rate and is designated for IMS signaling. Whereas QCI1 is guaranteed bit rate and is designated for voice over IP. This is what gives us our class identifiers. Now we see this as an example. We might be able to see some good examples of that. So here's that quality of service class. So now we're identifying just one of the tables. This is the QCI1 table as it's seen in the eNodeB's configuration manager, or what we call the site manager. So here are our parameters that are associated with QCI1. And each of the QCI tables would have their own set of configurations. So now here's where we can set quality of service for those different service flows, differentiated services. Now, when we talk about EPS bearers for conversational voice, we need to look at the EPS bearer for conversational voice. And when we set up control, so the subscriber is trying to come into the network, that's called admission control. We determine whether we have the resources or we do not. For voice over LTE, we have some limits for those flows. So by default, the maximum number of simultaneous QCI1 data radio bearers is 100. And then we have two additional parameters that can be used to adjust for buffer of incoming handovers to allow the incoming handovers to exceed this 100 limit.
Charles, I have a question. Here you talk about the Flexi BTS, and I'm a little bit familiar with the Flexi BTS being part of CDMA. How is the bearers also part of UMTS?
Okay, a bearer is the flow of data between a subscriber and the internet, basically. In the UMTS, we don't have a whole lot of flexibility in quality of service, differentiation of services between different functions. We can define them, but the QCI bearer, the QCI definition is a set of predefined forms of quality of service so that we can have a greater distinction than we had in UMTS. And the Flexi BTS is just our eNode B with LTE programming.
So in other words, instead of having Flexi BTS, it could say the eNode B takes the GBR signaling via S1 interface into account. Is that correct?
That is correct.
Oh, okay. That makes sense.
Okay, and now let's go on to the next slide. The next part of this. Admission control is tied to something called allocation retention priority, where I can determine whether I have priority of one subscriber over another. I have the capability of preemption. So that means when I'm congested and I have exceeded my values here, I have reached these values and no more, and the subscriber asks for some kind of service flow like conversational voice, it can be used to preempt subscribers. So in the tables for our ARP, inside our QCI tables, we're going to have a capability to preempt. So I can preempt something else if it's congested and I can preempt, or I am vulnerable to being preempted. So for example, we have a scenario where we have a full site. It has all the bearers, everything is in place, and it's all used. There are no resources available for an additional call. A subscriber connects to the site and asks for an emergency call. It's the highest priority. It is capable of preempting, and so it will preempt something that is the low priority, the lowest priority with the most amount of resources, and it will preempt that one. So in this case, low priority 14 with vulnerability, yes. Okay, and that way an emergency call will make it in and someone else will be asked to leave the site. And that's what this ARP is about in admission control. Now, in that, the scheduler will then look at the voice and will determine whether I can or can't, or what I'm going to do with the QCI. So this QCI1 bearer, so this is voice, it will look at that and it will give it a higher priority, not just by the priority, but it's also going to give me better, more, has a higher weight, I guess is the word I would use. But the weight of of its scheduling means it's more likely to be scheduled than a non-guaranteed bit rate, so that it can ensure the quality of the voice service. And this is actually what's allowing us to provide a quality voice, because we're putting it over a guaranteed bit rate, and it will not eliminate me from being able to do other functions, but it won't be affected by things like email. Now, there's one other thing that happens within this conversational voice. When we do the scheduling, unfortunately, we have large gaps in our audio. Now, I emphasize that by putting pauses between my words. So what does voice over LTE do? Well, we add something called the silence descriptor, or silence insertion descriptor, which says there's silence from this point for the next 20 milliseconds, 40 milliseconds, 100 milliseconds, whatever. And in that way, we can send a small packet instead of sending actual voice samples that are empty. And that way we use fewer over-the-air resources, allowing us to insert more and more subscribers in the same efficiently scheduled space. And the scheduler does this. And the subscriber can read these packets and know, okay, I'm just going to create white noise in the subscriber's ear so that they know that I haven't dropped the call.
Charles, could you please tell us how the scheduler schedules the QC1 bearer?
Yeah. Thanks. The QCI1 bearer scheduling happens to be the next topic, and let's look at that topic in a little bit of detail. Now, when we do scheduling of our subscriber actually will have been allowed to be scheduled in this time, transmit time interval, or TTI. And so once they have gotten into that point, it's in the list of the scheduling. We now have to prioritize our bearers. So the first thing that the scheduler will do is schedule LTE air interface signaling for that UE. That has the highest priority. It just also happens that when we are dealing with the priority, this priority, if we have it configured properly, this is also our SIP signaling that would be going through with that first step. After we prioritize, we do the signaling bearers, we will allocate the highest priority, or the weighted priority, of the guaranteed bit rate bearer for the subscriber. This happens to be QCI1, which is the highest priority guaranteed bit rate bearer. After we allocate one for voice, the QCI1, we will then go ahead and allocate more resources for the subscriber with whatever resources I have assigned to the subscriber by the scheduler. If there is anything left over, we will then assign any additional guaranteed bitrate bearer data to the subscriber. In this way, our non-guaranteed bitrate bearer will not be totally eliminated by possible guaranteed bitrate bearer data. Okay, so let's look at what is actually happening in that. Because when we're scheduling our subscribers and our data, we are going to add a delay target, which is controlled by the scheduler. Okay, so this delay target is a special term that we add to our normal proportional fare factor to determine what is our actual scheduling weight. So we take our delay target times the proportional fare, and I get the weight by which I'm going to organize each one of the bearers in for this subscriber individually. Now, this is a term. This is the uplink maximum packet aggregation, and the QCI1 tab delay target are the two values that we look at when we're working with this scheduling target. Now let's look at that in a little bit more graphical, and I like this picture because here each dot represents a TTI, a time when the subscriber is set to transmit. So the delay, the packet arrives at this point. Now, when the packet has arrived, but it has not been scheduled, okay, if it has not been scheduled, I am going to have a period of time where that factor is going to increase. That delay target factor is going to increase and increase and increase till at some point in time, particularly set by the delay target function, I have reached my maximum priority factor or the maximum delay target in the uplink. And at this point, I am trying to schedule it as much as I can, because if at this point I am reaching my actual total delay, what is the drop point? So once I get to this point, anything that exceeds that in being scheduled is now going to be dropped. So I'm measuring the time between when it arrived to when I actually transmit it. My scheduler is determining more, and so it is more and more likely in this area here, more and more likely to be scheduled. If it doesn't get scheduled at this point, then I'm going to have my delay target is I will have reached my max, but I also will not, I will schedule my, I will be more likely to schedule the resource over other resources because I have reached a higher priority, a higher weighting. I'm more likely to schedule because I've reached that high delay target. Back to the delay target times our weighting factor, it should, at this point, be higher than any other thing except for signaling. So signaling will always be going first, then our voice packet will be set.
The next topic is packet aggregation. Can you tell us what that is and how does it work?
Packet aggregation is really an ongoing addition to the scheduling function. We just talked about the packet delay. Well, in the packet delay, when we're looking at a VoIP packet, we have a VoIP packet where our packet comes in here and the next 20 milliseconds another one comes and then another one comes. That's our normal functionality. But we may have delays that are implemented, and this is where we add that jitter functionality. So functions of the jitter, and we can't assume that the subscriber will be able to receive this. What we're trying to do now is avoid too much jitter in our packet. But our scheduling request would come here. Our scheduling request has come, but we aren't scheduled until way out here. That's our big issue, is what happens in this case. We could just dump the packet frames, or we schedule all three of them in one uplink. And that's where packet aggregation comes in. We are scheduling it as soon as we can in the uplink. Okay, so let's look at what they mean. So now we're looking at how many packets can I schedule, or how important is it that I schedule the packets in the uplink at the appropriate time? Well, the conditions, the aggregations for packets are 2 aggregations. That means I'm putting together 3 voice packets or 2 voice packets in 60 milliseconds, plus the voice packet that is currently to be scheduled. So it ends up being 3 because it's a 60 millisecond delay. Here it's 4, and here it's 5 packets that are all being scheduled within that period. So this is affecting, so this is the parameter, uplink max packet aggregation, and what is the delay target, and each delay target sets, okay, back when we were looking at the delay, we're saying, okay, when do we start getting to the point where we need to drop the packet or not schedule it? So looking at this aggregation, so we could go back to the previous slide where we're looking at the aggregation back in our delay target. Now we're looking at not just one line here, but we're going to take and look at it from multiple line perspective. So here's our aggregation. So here we have no aggregation. That means I'm going to schedule it. It's really important that I schedule it, and I schedule it now. I don't wait till the next 20 milliseconds to schedule it. That would be aggregation level 2. And aggregation level 3 is I will just wait for a little while longer and schedule it. Now, part of what our criteria is it has to do with what is our quality of channel. So what is the quality of my channel? So when I have a 50 millisecond delay and then I have a delay target of 60, so I've actually reached 50 milliseconds, delay target is 60, I'm in an aggregation level 3 for my to transmit my my packets, my set group of packets. Now looking at it a little bit more, packet arrived, I waited, I did not transmit. That's where we're getting into our delay target being closer to that 80 milliseconds by default. Okay, so we're aggregating true. That means our curve here says that we're here on our target. We're 30 milliseconds into after having arrived at we have 30 milliseconds left after the packet has arrived. We have 30 milliseconds to deliver that, and if we have good signal, then we'll probably wait and deliver it at this point. So what do we have? Okay, here is no aggregation. This is when I have very poor channel conditions. That means I'm going to aggregate. I'm going to send the packet as soon as I can. I do not delay it at all until the next packet. And the aggregation level 2, I'm going to delay it, and then I'll accumulate multiple packets and send it as one single allocation of resources in the air interface. If I wait longer, then I get to aggregation level 3. This is when I have really good packets, really good conditions. That means I'm not worried about having retransmissions because I have really good conditions. Therefore, I will be able to send 3 packets together at the same time. So I'll have the one that came in here, the 20 millisecond delay, then I'll have plus the one that's at the 60 millisecond plus the ones at 40. But that's because I have excellent conditions and I'm just sort of waiting a little longer for me to deliver the packet. But that way I can deliver 3 at one time. Okay, now the way we do that is we're taking that packet delay function and we're adding a little bit more functionality to that to determine what is my aggregation level. Based on the aggregation level, I'm going to determine what my target downlink, and this is for the downlink one, and the other one can be used for the uplink as well. We're going to have a target to go up, and as our conditions get better, our aggregation gets lower. If our conditions our aggregation is higher. If our conditions get worse, our aggregation goes lower. So this is based on our actual channel conditions. So the radio conditions are going to determine what I choose for my delay target to determine whether I can or can't aggregate my packets.
So now we understand what is packet aggregation and how it works. Can you share with us the parameters associated with it?
There are really very few parameters that we're going to be dealing with when it comes to conversational voice. There are only 3 parameters specifically that are focused on radio on conditions about the QCI1 bearer. And we've kind of seen them already. So the maximum number of QCI1 data radio bearers on one cell. Then I have 2 parameters that deal with the handover limits that allow me to stretch that handover limit up to help me be able to handle incoming handovers. So incoming to the cell. So they would exceed. So it would be this parameter plus the greater of both of these parameters. And that would be the actual hard limit that we would set in the site. And these are parameters I can change. Some of the parameters we talked about, delay target, that would be in the QCI table. Those parameters would be determining for some of the stuff that we've been talking about for QCI1 scheduling weights. And they affect the scheduler more than they affect radio admission control.
Are there any KPIs with EPS bearers for conversational voice?
Absolutely. In fact, there's a whole ton of them. We have accessibility parameters, which deal with setting up the quality of service 1 class bearers. What is the success ratio? So here are the KPIs for accessibility. We have a set for reliability. So how often or what we do for dropping our bearers. Can we drop if they are dropped or not? How long were they? How long did we hold them? So retainability for our bearers. We also have usage. Here's where we actually track how many we used in the downlink, how many we used in the uplink. What is the active time for the QCI1 bearer minimums? What is the throughput? The average scheduled throughput? What is the discard ratio for errors? Like the PDCP and the PDCP layer. What is the IP throughput? The average IP throughput, and what is some of the maximum number of QCI1 bearers in this cell. So those are the usage ones. The last set is integrity. Our integrity has to do with what is the loss ratio of our data. This isn't the drop ratio. This is the loss of actual data. When we exceeded that delay target, when did we drop it? Or due to congestion, when was I not able to process the data in the eNode B to deliver to the subscriber? This is true in the downlink. This is also true in the uplink, where we have a loss ratio in the uplink. And all we're doing there is processing how much did we not get because of radio conditions that caused us to try to retransmit and exceeded the retransmission of the hybrid ARQ.
How do we handle emergency calls?
Emergency calls, in particular on the VoLTE side, so voice over IP, use the IMS for its emergency call handling. So there are really a couple things that we need to look at. First of all, an emergency session is admitted with high priority for the subscriber. So the subscriber with its high priority will be allowed into the network, and we set what the emergency thresholds are for that subscriber. Now, in emergency sessions, we are going to prioritize them over regular or normal sessions. And this has to do with the signaling and priority the ARP that we talked about previously. We also have to take into account that we support all mobility, whether we do it inter-enode B, intra-enode B, inter-frequency, intra-frequency, over the X2, over the S1. Those are the mobilities that are handling within LTE. But if we're doing it in between LTE and other technologies, there's really only two things that we can do. We could release the subscriber and redirect them to another technology with high priority, also known as circuit switch fallback with emergency. Or if we end up having poor coverage and we need to hand over to another technology, we use this single radio voice call continuity, which will allow me to perform a handover with the voice call in progress. Now, there are two types of subscribers that we're going to look at. First of all, we're going to look at what is a normal UE when it is performing an emergency session. What is it going to do with a normal emergency session? And then we have the subscriber that doesn't have a SIM card or something like that, where it is limited service or it's in roaming coverage that isn't a agreed upon partner. How do we make a emergency call in limited service scenarios? So that's the two scenarios that we'll be looking at. So two types of variants of emergency sessions. The subscriber camps on a cell normally. It is registered on its home public land mobile network, and the UE is supported by the cell. That means the subscriber knows and it enters the correct subscriber function. It knows the correct PIN number and it dials the emergency number, 112, 911, whatever happens to be the emergency number, it will connect in. That's the first subscriber function. The limited is one who doesn't have the right number and it doesn't have, it needs to make an emergency call. So for example, many times on our phones, if our phone is locked, there is still the possibility of making an emergency call with the phone. So if someone is hurt or injured or something, we can pick up that person's cell phone and make the emergency call. That might be the case when we are in limited capability, limited coverage. Now, when we do this, the subscriber will automatically attach to an emergency APN. Now, that APN means access point name. What that really is the PGW that will associate it with the emergency call serving call function in the IMS so that the subscriber can make an emergency call.
Can you go over the call flows for normal and limited service?
A call flow for a normal subscriber. So the subscriber is registered on the network. He may be idle or he may be active. Okay, so it doesn't really have to do with the active or idle, except if I'm active, I don't have to perform the random access procedure. So I'm going to start, I dialed the 911 or the 112 or whatever happened to be the emergency numbers of the country where that subscriber is. The subscriber will perform the random access procedure to establish the the RRC connection. In the last message, this is what we call message 3, the subscriber will send in an RRC connection request with the reason being emergency. The eNode B sees it as an emergency and will establish the RRC connection setup, will forward that to the MME, the mobility management entity, who will go ahead and establish the EPS bearers for the subscriber on the emergency APN. Now we'll go ahead and go through that rack, which is radio access control. So if I have a congested eNode B, the eNode B may preempt other subscribers at this point to allow me to establish the default bearer, the QCI1 bearer, and the QCI5 bearers for the subscriber. But we will do it. We will register with the emergency APN, which is actually one of the set of parameters. So we're connecting not to our normal PGW. We are now connecting to a different PGW, which is connected to the emergency call serving call function inside the IMS, or the IP multimedia subsystem. Okay, so now once we've established this signaling, we set up the initial bearer, QCI5, and this is the way that works. So if I have a system where the subscriber is already connected, I'm going to go ahead and do an emergency call. So this first one was I'm coming out of idle into active. In the active one, I'm already active. I'm going to go ahead and transfer information up in the uplink saying, hey, I have an emergency. We forward that to the MME, which then sets up, again, radio access control based on allocation retention priority. We'll go ahead and establish the new signaling QCI5, but this is QCI5 to the new emergency access point name, the APN. And then we'll go ahead, once we have that set up, we'll go ahead and perform procedures for radio access control for QCI1 bearer, again, based on allocation retention priority, so that the subscriber can preempt someone. Again, either place, here or here, I may be preempting a lower priority subscriber, whether they be data or voice. Now, once I've done that, I set up the QCI5, then I set up the voice call via the QCI5, all of the SIP signaling that we saw in a previous chapter. Okay, now looking at the limited subscriber. The limited subscriber is not normally connected. It's listening to the cell because I don't have anywhere else to go. So what do? I'm listening to the cell. It does support emergency IMS, so I will stay in what we call camp on the cell. When that happens, so I don't have service from my normal provider, or I don't have a USIM or something along that line, therefore, I don't have service, yet I can initiate an emergency call. So I've read the broadcast channel, I perform the random access procedure, I send in the RRC connection request with reason emergency, we perform radio access control based on the emergency cause, we establish the RRC connection, we forward to the MME, who will then connect me to the emergency access point name. When the context setup comes back from the emergency access point name to establish the QCI5, we'll go ahead and create a QCI5 bearer specifically to that emergency access point name. This will go ahead and go through a security authentication type setup so that the system knows how to perform what we need to do. At the end of it, we will go ahead and create the QCI5 bearer here. We'll then go ahead and do the signaling across the QCI5 bearer. That's all the bearer setup. And then we'll go ahead signal, and then we'll go ahead through the procedure like this RRC connection reconfiguration to establish the dedicated QCI1 bearer for that emergency call. So every time. Okay, so we're going to establish the QCI5 bearer here. And then later on, we will go ahead and go through the RRC connection reconfiguration to establish and activate the emergency QCI1 bearer. The difference is, instead of going to a regular IMS, we are going to a dedicated emergency IMS for this call.
Now that you've given some call flow examples, what parameters do we need to configure the emergency IMS sessions?
Well, there's a couple parameters that we need to be aware of. First of all, we have to define what is the emergency access point name. So we have to define that. That's a different set of parameters. But the ones that we really are focusing on are the ones that deal with limiting or radio access control of the cell. So first of all, we have to activate the IMS emergency for release 9 subscribers, because a release 8 subscriber did not have the capability of performing emergence, or it cannot perform voice. So what would happen with a release 8 subscriber is it would be sent, so it would be redirected to another technology. Whereas a release 9 subscriber, which does support voice over LTE, would be able to enable the feature. Now, once it's enabled, the number of emergency sessions I can have is based on partly on bandwidth. Now, these are our recommended numbers for bandwidth for emergency sessions. These are sessions over and above the sessions that we would have for regular QCI-1. So we would be able to have a certain limited number of QCI-1 emergency sessions that would be on top of the QCI-1 bearers for regular calls. We also have to say, is it enabled? So the two parameters, the enabling is activate IMS emergency session release 9, and then how many additional emergency sessions do I allow? By default, we have it set to 70. Remember, it is really truly bandwidth dependent.
What are the KPIs associated with IMS emergency sessions?
There's just a few, not a lot. We are dealing with the KPIs. We have some fallback attempts. That would be for the non-Release 9 subscribers. We can actually know when we sent the subscriber to other technologies. We have what is the success ratio for IMS sessions. That means I have to have a voice over LTE system enabled. How many attempts for handovers during the emergency session? How many times, so the success ratio of the IMS, the handovers. What are additional setup attempts for IMS? So I may already be in a call and then I trigger an IMS, or I may be in a session and I trigger some kind of IMS functionality for emergency. What are any failures that we had? Those are KPIs that we have. And we have a KPI that specifically focuses on the call setup attempts or the RRC setup. That's the signaling attempts that are emergencies. Understanding that this one here is tied to both the fallback and the IMS emergencies. So this is both. And then we'll have, why did we reject the connection setup? If I am totally overloaded and I have every single resource in play, I can reject a call. The subscriber may end up going to another technology or whatever to perform the call, but that is another one of our KPIs.
Thank you, Charles, for going through Voice over LTE radio enabling features with us. It was a very interesting session.
Thank you.